Our journey begins in a place of familiarity, a celestial neighborhood anchored by a single central star. This star, the Sun, is a sphere of incandescent gas, a body of immense scale that governs the motion of all that surrounds it. Its diameter stretches approximately 864,000 miles, a distance so vast that over 100 Earths could be lined up across its face. The Sun's mass is the primary factor that holds our solar system together, exerting a constant gravitational pull on every planet, moon, and asteroid. It accounts for more than 99% of all the mass in this system. This gravitational influence is the silent, unseen force that defines the orbits of the worlds that circle it, creating a stable and predictable cosmic dance. At its surface, the Sun maintains a temperature of about 9,940 degrees Fahrenheit. This immense heat is generated by a process deep within its core, a nuclear furnace where hydrogen atoms are fused into helium. This process releases a steady stream of energy, which radiates outward as the light and warmth that permeate the solar system, a constant and unwavering presence. Closest to the central star is Mercury, a small, rocky world. It follows an elliptical path at an average distance of 36 million miles from the Sun, completing a single orbit in just 88 Earth days. Its surface is a landscape of craters and plains, baked by the Sun's proximity during its long day and frozen in the deep cold of its equally long night. Next in this slow procession is Venus, a world shrouded in a thick atmosphere of carbon dioxide. It orbits at a distance of about 67 million miles from the Sun. The dense atmosphere traps heat, resulting in surface temperatures that are higher than Mercury's, a constant and uniform heat that envelopes the entire planet, making its surface the hottest in the solar system. Our own world, Earth, occupies the third position in this orbital sequence, residing at an average distance of 93 million miles from the Sun. This specific distance allows for conditions where water can exist in liquid form on the surface, a key ingredient for the forms of life that have developed here. It moves through space at a speed of over 67,000 miles per hour, completing its journey around the Sun once per year. Beyond Earth lies Mars, the fourth planet, often called the red planet due to the iron oxide prevalent on its surface. It orbits at an average distance of 142 million miles from the Sun. Mars is a world of stark contrasts, with polar ice caps, vast canyons, and dormant volcanoes, all existing under a thin atmosphere that offers little protection from the cold of space. Separating the inner, rocky planets from the outer gas giants is the asteroid belt. This is not a dense, crowded field, but a vast, diffuse region of space containing millions of rocky bodies. They are remnants from the early solar system, pieces that never coalesced into a planet, each one following its own silent orbit around the Sun. The first of the outer worlds is Jupiter, a colossal giant of gas and liquid that contains more mass than all the other planets combined. Its diameter is over 86,000 miles, and it orbits at a serene distance of 484 million miles from the Sun. Its atmosphere is a tapestry of swirling cloud bands and storms, including the Great Red Spot, a persistent storm larger than Earth itself. Further out, we encounter Saturn, the sixth planet, distinguished by its magnificent system of rings. Orbiting at a distance of 886 million miles from the Sun, Saturn is another gas giant, though less massive than Jupiter. Its rings are not solid, but are composed of countless individual particles of ice and rock, each one in its own orbit, forming a shimmering, flat disk. The journey continues to Uranus, the seventh planet from the Sun, orbiting at a remote distance of nearly 1.8 billion miles. This world is an ice giant, composed of a higher proportion of ices like water, ammonia, and methane. Uniquely, Uranus is tilted on its side, causing it to roll along its orbital path like a ball, resulting in extreme seasons that last for decades. Neptune is the eighth and most distant known planet in our solar system, circling the Sun at an average distance of 2.8 billion miles. It is another ice giant, similar in composition to Uranus, with a dynamic atmosphere of vivid blue clouds and the fastest winds in the solar system. Its journey around the Sun is a slow and stately procession, taking nearly 165 Earth years to complete. Beyond the orbit of Neptune lies a distant, icy region known as the Kuiper Belt. This is a vast, disc-shaped zone, home to countless small, frozen bodies, including dwarf planets like Pluto. It is a relic from the formation of the solar system, a cold and dark frontier where the sun's light is faint and its gravitational influence begins to wane. Enveloping the entire solar system is the theoretical Oort cloud, an immense, spherical shell of icy objects thought to be the most distant reservoir of comets. It is believed to extend nearly a quarter of the way to the next nearest star, marking the true outer boundary of our sun's gravitational kingdom. Its existence is inferred, a final, unseen layer to this stable system. The scale of this system is defined by these immense distances. Light itself, the fastest thing in the universe, takes more than 8 minutes to travel from the sun's surface to Earth. To reach Neptune, that same light must travel for over 4 hours. It is a system built upon a foundation of vast, quiet space, punctuated by these orbiting worlds. Each planet follows a path dictated by gravity, a fundamental force of nature. This force is like an invisible thread, connecting each world to the sun, ensuring their orbits are stable over billions of years. The process is mechanical and predictable, a cosmic clockwork operating on the grandest of scales, without haste or deviation. The space between these worlds is not entirely empty. It is a near-perfect vacuum, filled with a tenuous medium of particles known as the solar wind. This is a constant stream of charged particles flowing outward from the sun, traveling through the entire system and interacting with the magnetic fields of the planets it encounters. This entire structure, from the central star to the outermost cloud, exists within a larger context. It is a single star system among billions, located in a quiet, suburban arm of a vast spiral galaxy. It is a small, orderly island of matter, drifting serenely through the immense emptiness of interstellar space. The arrangement of the planets follows a certain logic. The inner worlds are small, dense, and rocky, having formed in the hotter region closer to the sun where lighter gases were boiled away. The outer worlds are large and gaseous, having formed in the colder regions where they could accumulate vast atmospheres of hydrogen and helium. The temperatures of these worlds are a direct consequence of their distance from the Sun. Mercury's surface can swing from over 800 degrees Fahrenheit during the day to minus 290 degrees at night. In contrast, the cloud tops of distant Neptune exist in a perpetual deep freeze of around minus 350 degrees Fahrenheit. The colors we perceive in the planets are a result of their composition. Mars's reddish hue comes from iron-rich dust. Jupiter's bands of cream and caramel colors are a result of different chemicals at different altitudes in its atmosphere. Neptune's striking blue is caused by methane gas absorbing red light. Each world is a self-contained physical system. Jupiter possesses a powerful magnetic field, a product of the motion of liquid metallic hydrogen deep within its interior. This field creates intense radiation belts and beautiful, shimmering auroras at its poles, much like the auroras seen on Earth, but on a far grander scale. Saturn's rings, while appearing solid, are a dynamic and complex system. They are incredibly thin relative to their width, like a sheet of paper the size of a city. The particles within them are constantly, gently colliding, organized into thousands of individual ringlets by the gravitational influence of Saturn's many small moons. The concept of a year is simply the time it takes for a planet to complete one full orbit around the Sun. An Earth year is 365 days. A Martian year is almost twice as long, at 687 days. A year on Neptune, due to its vast orbit, is equivalent to nearly 60,000 Earth days, a timescale that stretches human comprehension. The planets also rotate on their axes, creating the cycle of day and night. A day on Jupiter is incredibly short, lasting less than 10 hours. In contrast, a day on Venus is longer than its year, with the planet rotating so slowly that one sunrise to the next takes 243 Earth days. This solar system is a place of profound silence. Sound requires a medium to travel, and the vacuum of space provides none. The vast movements, the orbital journeys, and the slow rotations all occur without a whisper, a silent gravitational ballet that has been unfolding for more than 4.5 billion years. The system is ancient, It formed from a vast rotating cloud of gas and dust called a solar nebula. Gravity caused this cloud to collapse in on itself, forming the Sun at its center, while the remaining material flattened into a disk from which the planets, moons, and asteroids gradually accreted, like dust bunnies forming under a bed. The process of planet formation was slow and methodical. Tiny grains of dust stuck together, forming larger clumps, which in turn attracted more material through gravity. Over millions of years, these clumps grew into planetesimals and eventually into the full-sized planets we observe today, each one clearing its own orbital path. The stability of this system is a delicate balance between the forward momentum of the planets and the inward pull of the Sun's gravity. If the planets moved slower, they would fall into the Sun. If they moved faster, they would escape its gravity and fly off into interstellar space. The current state is one of long-term, predictable equilibrium. Thus, we have established our starting point, a single star orbited by 8 distinct worlds, each with its own physical characteristics, all held together by the universal law of gravitation. It is a system of immense space and immense time, a foundation from which we can begin to expand our perspective outward into the galaxy. Having established the boundaries of our solar system, we now drift outward into the space between the stars. To measure these new, far greater distances, we must adopt a new scale. This scale is based on the speed of light, which travels at a constant 186,282 miles per second. A light year is simply the distance that a beam of light travels in one terrestrial year, a measure of approximately 5.88 trillion miles. Our Sun's nearest stellar neighbor is a small, dim star named Proxima Centauri. It lies at a distance of 4.24 light-years, which translates to roughly 25 trillion miles. This gap between our Sun and the very next star is more than 4,000 times the diameter of our entire solar system. It is a profound emptiness, a defining characteristic of interstellar space. Proxima Centauri is part of a triple star system, which also includes the brighter pair of Alpha Centauri A and B. These two stars orbit each other closely, while the dim Proxima Centauri orbits this central pair at a great distance. They exist as a small, gravitationally bound family, a common arrangement for stars throughout the galaxy, moving together through the void. Beyond this first outpost, other stars are scattered at similar, immense intervals. At a distance of 5.96 light-years lies Barnard's star, a low-mass red dwarf, older than our own Sun and moving through space at a relatively high velocity. It is a quiet star, emitting far less light and energy than our own, a faint ember in the cosmic darkness. Continuing our outward survey, we would encounter Wolf 359 at 7.8 light-years, another faint red dwarf. At 8.6 light-years is the binary star system Lalande 21185. The Sirius system, containing the brightest star in Earth's night sky, lies at 8.6 light-years as well. Each star or system is an island of matter, separated by trillions of miles of near-perfect vacuum. This methodical listing of neighbors continues. The Luton 726-8 system is 8.7 light-years away. Ross 154 is at 9.7 light-years. Ross 248 is at 10.3 light-years. Each name and number represents another sun, another anchor of gravity in the vastness, their light taking many years to cross the gulf that separates us from them. The space these stars inhabit is not a complete void. It is filled with a tenuous substance called the interstellar medium. This medium is an extremely diffuse mixture of gas, primarily hydrogen and helium, and tiny particles of dust. On average, the density is only about 1 atom per cubic centimeter, a vacuum far more empty than any that can be created in a laboratory on Earth. Our solar system is currently passing through a specific region of this medium known as the local interstellar cloud. This is a wisp of slightly denser gas, approximately 30 light-years across. The Sun's own magnetic field and solar wind create a protective bubble around our system, called the heliosphere, which pushes back against this thin external medium. This local cloud is, in turn, situated within a much larger structure known as the local bubble. This is a vast region of space, roughly 300 light-years in diameter, where the interstellar gas is significantly hotter and less dense than the surrounding average. It is thought to have been carved out long ago by the stellar winds and supernova events of massive stars that have since faded away. The formation of this bubble was not a violent event in the human sense, but a slow, million-year process of energy dispersal. The energy from ancient stars pushed the surrounding gas outward, creating a low-density cavity. Our Sun and its neighboring stars are now simply drifting through this cleared-out region, like boats on a calm and exceptionally wide sea. The stars within this local neighborhood are not stationary. They are all in constant motion, each following its own vast orbit around the center of our galaxy. Their relative positions shift over immense timescales. In tens of thousands of years, the pattern of constellations we see in the night sky will have slowly and imperceptibly warped into new and unfamiliar shapes. The motion is complex. While orbiting the galactic center, the stars also move relative to one another, some slightly faster, some slower, some moving slightly inward, others outward. This slow, three-dimensional drift is akin to the movement of individual particles in a vast, slow-flowing river, all moving in the same general direction but with minor local variations. The concept of a neighborhood, therefore, is temporary. The stars that are our neighbors today were not our neighbors in the distant past, and they will not be in the distant future. The community of stars is ever-changing, a silent, swirling dance that unfolds over eons, governed entirely by the force of gravity on a galactic scale. This is the immediate environment of our Sun, a collection of scattered stars, moving together through a vast, low-density bubble of interstellar gas, all participating in a grand, slow orbit around a distant galactic core. It is the second step in our journey of scale, a bridge between the familiar solar system and the unimaginable expanse of the galaxy itself. We now expand our view beyond the local stellar neighborhood to encompass the entirety of our home galaxy, the Milky Way. This is a colossal structure, a gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and dark matter. Its visible diameter is estimated to be approximately 105,700 light-years across. The shape of our galaxy is that of a barred spiral. It consists of a central, bar-shaped core of stars, surrounded by a flat, rotating disk. This disk is where the majority of the galaxy's star formation takes place, and it is organized into several distinct spiral arms. Our Sun is located within one of these arms, about two-thirds of the way out from the galactic center. The galactic disk, while immensely wide, is relatively thin. Its average thickness is only about 1,000 light-years. This proportion is similar to that of a phonograph record or a dinner plate, a vast, flat plane of matter rotating in space. It contains the younger, brighter stars of the galaxy, along with the clouds of gas and dust from which new stars are born. At the very heart of the galaxy lies the central bar and a dense region known as the galactic bulge. This area is packed with a much higher concentration of stars, most of which are older and redder than our Sun. The environment here is far different from our quiet suburban location, with stars much closer to one another, their gravitational influences more complex and intertwined. At the precise center of this bulge resides a supermassive black hole named Sagittarius A star. This is not a destructive void, but rather a point of immense mass that serves as the galaxy's central gravitational anchor. It has a mass equivalent to about 4 million suns, yet its physical size is compact, a silent and stable hub around which the entire galaxy revolves. The spiral arms are not solid, fixed structures. They are best understood as density waves, similar to a traffic jam on a highway. As gas, dust, and stars move in their orbits, they pass through these slower-moving waves of higher density. Inside the arm, the compression of gas can trigger the formation of new stars, which is why the arms appear so bright and distinct. Our solar system resides within a minor arm known as the Orion Cygnus arm, or simply the Orion Spur. It is a smaller structure located between two of the major arms, the Sagittarius arm and the Perseus arm. Our position is relatively calm and stable, far from the more chaotic and energetic regions of the major arms and the galactic core. The number of stars within the Milky Way is staggering. Current estimates suggest there are between 100 billion and 400 billion stars. This is not a precise count, but an approximation based on the galaxy's mass and luminosity. For every single human who has ever lived, there are at least 10 stars in our galaxy alone. Surrounding the entire disk is a vast, spherical structure called the galactic halo. This is a sparse, ancient region containing scattered old stars and large clusters of stars known as globular clusters. The halo is mostly empty space, but it is also believed to contain the vast majority of the galaxy's mass in the form of a mysterious, invisible substance called dark matter. The halo of dark matter is a crucial component of the galaxy. It is a gravitational scaffold, an unseen structure whose mass holds the entire galaxy together. Without the extra gravitational pull of this dark matter, the stars in the outer regions of the disk would be moving too fast, and they would simply fly off into intergalactic space. The galaxy's rotation is a clue to this invisible mass. The entire Milky Way galaxy is in motion. It does not sit still in space. It rotates, with the Sun and our solar system completing one full orbit around the galactic center approximately every 230 million years. This journey is known as a galactic or cosmic year. Since its formation, our Sun has completed this orbit only about 20 times. The process of star formation within the galaxy is continuous. In vast, cold clouds of molecular gas, gravity slowly pulls material together into dense clumps. As these clumps contract, they heat up, eventually becoming hot enough in their cores to ignite nuclear fusion. This is the birth of a star, a process that has been repeating throughout the galaxy for billions of years. Conversely, stars also reach the end of their lives. For stars like our Sun, this is a gentle process of swelling into a red giant and then slowly shedding its outer layers to form a planetary nebula, leaving behind a small, dense core called a white dwarf. The process is a slow, gradual transformation over millions of years. For stars much more massive than the Sun, the end is more energetic. They end their lives in a supernova event, a process that releases immense amounts of energy and heavy elements back into the interstellar medium. This enriched material then becomes part of the next generation of stars and planets. It is a grand cycle of cosmic recycling. These supernova events, while energetic, are sanitized by distance. They are localized physical processes, and from our vantage point tens of thousands of light-years away, they pose no threat. They are simply part of the galaxy's metabolism, the mechanism by which it enriches itself with the chemical elements necessary for forming rocky planets and, eventually, life. The galaxy is a self-contained ecosystem. It creates stars from gas, and when those stars end their lives, they return processed material back into the galactic environment. It is a system in a state of slow, dynamic equilibrium, constantly changing on timescales of millions and billions of years, but maintaining its overall structure and form. Looking at the Milky Way from the outside, it would appear as a luminous, pinwheeling collection of light against the blackness of intergalactic space. A beautiful, serene structure, turning silently, its billions of stars moving in a coordinated, gravitational dance of immense scale and complexity. This is our home on the grandest scale yet. We now zoom out once more to view our Milky Way galaxy not as an entire universe unto itself, but as a single member of a small community of galaxies. This community is known as the local group. It is a collection of more than 50 galaxies, bound together by their mutual gravitational attraction, occupying a region of space roughly 10 million light-years in diameter. The local group is dominated by two large spiral galaxies, our own Milky Way and the Andromeda galaxy. Andromeda, also known as M31, is the largest member of the group. It is located approximately 2.5 million light-years away from us, a distance so great that the light we see from it tonight began its journey when early human ancestors were first walking the Earth. Andromeda is slightly larger and more massive than the Milky Way, containing perhaps as many as 1 trillion stars. Through a telescope, it appears as a faint, elongated smudge of light, a celestial island of stars similar to our own, but seen across an immense chasm of intergalactic space. It is the most distant object that can be seen with the naked eye. The third largest member of the local group is the Triangulum galaxy, or M33. It is another spiral galaxy, but significantly smaller than either the Milky Way or Andromeda. Contains a mere 40 billion stars and lies about 3 million light-years from us. The rest of the local group's members are much smaller dwarf galaxies. These dwarf galaxies are small, faint collections of a few billion stars or less. Many of them are in orbit around the larger galaxies, much like moons orbiting a planet. The Milky Way has several such satellite galaxies, the most famous of which are the Large and Small Magellanic Clouds, visible only from the southern hemisphere. The entire local group is held together by gravity. Each member galaxy exerts a gravitational pull on every other member. The result is a complex dance where galaxies orbit a common center of mass. The smaller dwarf galaxies orbit the larger spirals, and the two large spirals, the Milky Way and Andromeda, are themselves moving toward each other. This motion will result in a future event known as the merger of the Milky Way and Andromeda. This is not a collision in the conventional sense. Due to the vast distances between individual stars, when the two galaxies merge, it is exceedingly unlikely that any two stars will actually collide. The event is more like two immense clouds of smoke slowly intermingling. This merger process will unfold over billions of years. As the two galaxies approach, their gravitational forces will begin to distort their shapes, pulling out long streams of stars and gas. They will pass through each other several times, their structures disrupted and reformed with each pass, until they eventually settle into a single, larger, elliptical galaxy. This future galaxy, sometimes unofficially named Milkomeda, will be the result of a calm, gravitational settling process on an unimaginable timescale. The event is a natural part of galactic evolution. It is a quiet, creative process, triggering a new burst of star formation as the gas clouds from both galaxies are compressed and combined. The space between the galaxies in the local group is known as the intergalactic medium. It is even more tenuous than the interstellar medium within the galaxies, a near-perfect vacuum containing only a few scattered atoms per cubic meter. It is a realm of profound emptiness, across which the faint light of distant galaxies must travel for millions of years. The local group itself is not isolated. It is a small, relatively unassuming cluster of galaxies in a much larger cosmic structure. It drifts through space as a single, gravitationally bound unit, its member galaxies all moving together on a shared trajectory through the universe, a tiny family on a vast cosmic journey. By observing the local group, we learn that our galaxy is not unique. It is a common type of structure in the universe, and its destiny is intertwined with that of its neighbors. The scale has now expanded from the distance between stars to the distance between entire star systems of billions, a perspective that renders our solar system an infinitesimally small speck. This view provides a sense of cosmic community. Our galaxy is part of a local family, governed by the same physical laws that dictate the orbit of the Earth around the Sun. The force of gravity, acting over millions of light-years, choreographs the slow and stately dance of galaxies, a process of change and evolution that unfolds on the grandest of scales. Our perspective expands one final time for this phase, moving beyond our immediate galactic family to the larger association to which it belongs. The local group is not an island, but is itself a small part of an even grander structure, the Virgo supercluster. This is a massive concentration of galaxy groups and clusters, spanning a diameter of approximately 110 million light-years. A supercluster is not a single, gravitationally bound object like a galaxy or a galaxy group. Instead, it is a vast, sprawling collection of galaxies that are more concentrated in one region of space than in others. They are all generally moving away from each other due to the expansion of the universe, but their local density is still much higher than the cosmic average. The heart of our supercluster is the Virgo cluster, a massive and dense collection of over 1,300 galaxies, located about 54 million light-years away from us in the direction of the constellation Virgo. This cluster acts as the dominant gravitational center of the supercluster, its immense mass influencing the motion of all the surrounding galaxy groups, including our own. Our local group is located on the outskirts of the Virgo supercluster, a small, outlying group being gently pulled toward the massive Virgo cluster at the center. This motion is not a rapid fall, but a slow, cosmic drift, an infall velocity of a few hundred miles per second, superimposed on the overall expansion of the universe. The Virgo supercluster contains approximately 100 galaxy groups and clusters similar to our own. It is a vast cosmic city, and our local group is merely one of its quiet, suburban neighborhoods. The space within the supercluster is filled with these galactic systems, like islands of light separated by vast, but not infinite, stretches of intergalactic void. At the center of the Virgo cluster itself lies a giant elliptical galaxy known as Messier 87, or M87. This galaxy is far more massive than either the Milky Way or Andromeda, containing trillions of stars. It is an older, more settled galaxy, composed mostly of ancient stars and possessing very little gas for new star formation. The structure of a supercluster is not spherical, but is instead filamentary and web-like. The galaxy groups and clusters are not distributed randomly, but are arranged in long chains and flattened sheets, separated by large, relatively empty regions of space known as voids. This arrangement is a fundamental characteristic of the universe on its largest scales. The Virgo supercluster is just one of many such structures in the observable universe. When we map the positions of galaxies in 3 dimensions, we see that they form a vast, interconnected network, often called the cosmic web. The superclusters are the dense nodes and bright filaments in this web, while the voids are the immense, dark gaps between them. Observing this structure provides a profound sense of scale. The journey from our Sun to its nearest neighbor, Proxima Centauri, is an immense leap. The journey from our Sun to the center of our galaxy is 1,000 times greater still. And the journey from our galaxy to the center of the Virgo supercluster is another 1,000 times greater than that. Each step outward reveals that the previous structure was but a small component of a larger system. The planet is part of a solar system. The solar system is part of a stellar neighborhood. The neighborhood is part of a galaxy. The galaxy is part of a group. And the group is part of a supercluster. The pattern is one of nested hierarchies, scaling up to sizes that defy easy comprehension. This grand structure, the Virgo supercluster, is the largest local feature in our cosmic environment. It represents the limit of what we might call our cosmic continent. Beyond it lie other superclusters and immense voids, all part of the same universal cosmic web, stretching on for billions of light-years in every direction we look. The light we receive from the Virgo cluster began its journey over 50 million years ago, at a time when dinosaurs had long vanished but the age of mammals was just beginning on Earth. We are seeing these distant galaxies as they were in the remote past, their light serving as a form of time travel, connecting us to the deep history of the cosmos. We now adjust our perspective to a scale where even the Virgo supercluster becomes a mere component of a yet larger system. This system is Laniakea, a Hawaiian name meaning immeasurable heaven. It is not a structure held together by gravity, but rather a collection of galaxies all flowing toward a common destination, a shared basin of gravitational attraction. Laniakea is defined by the motion of galaxies. By mapping their velocities, astronomers can trace the gravitational contours of the universe, much like mapping a watershed on Earth. All of the galaxies within Laniakea, including our own Milky Way, are flowing inward toward a single point, a vast gravitational anomaly known as the Great Attractor. The Great Attractor is not a single object, but a diffuse concentration of mass located roughly 150 million light-years away. Its nature remains partially obscured by the disk of our own galaxy, but its immense gravitational pull is evident in the coordinated motion of 100,000 nearby galaxies. It is the center of our local cosmic river. The scale of Laniakea is immense, spanning over 520 million light-years. It contains the mass of 100 quadrillion suns, distributed among the 100,000 galaxies that participate in this large-scale flow. Our Virgo supercluster is just one of many tendrils, one branch of this vast celestial river system, slowly making its way downstream. Visualizing Laniakea requires letting go of the idea of a distinct, bound object. It is a structure of motion, a region of shared destiny. The galaxies within it are like raindrops on a vast, invisible landscape, all following the path of least resistance carved by the underlying distribution of mass. A silent, coordinated drift that unfolds over hundreds of millions of years. As we pull our view back even further, we see that structures like Laniakea are not isolated. They are the bright, dense threads in a vast, interconnected cosmic web. The universe on its largest scales is not uniform, but is organized into an intricate, foam-like pattern of massive structures and near-perfect voids. The brightest and largest of these structures are the galactic filaments and great walls. These are colossal chains of superclusters, stretching for hundreds of millions, and sometimes billions, of light-years. They are the largest known structures in the universe, great rivers of galaxies that outline the boundaries of the immense cosmic voids. One of the first such structures discovered was the CFA-2 Great Wall, a filament of galaxies measuring over 500 million light-years long and 300 million light-years wide, but only 16 million light-years thick. It is a flattened sheet of galaxies, a cosmic ribbon unfurled against the darkness of the intergalactic medium. An even larger structure is the Sloan Great Wall, located about 1 billion light-years from Earth. This is a galactic filament with a length of 1.38 billion light-years, a truly staggering collection of superclusters that, when discovered, represented the largest known object in the cosmos. It is a testament to the hierarchical nature of cosmic structure. The current record holder for the largest structure is the Hercules Corona Borealis Great Wall. This is a vast concentration of galaxy clusters that stretches for more than 10 billion light-years, representing more than 10% of the diameter of the entire observable universe. It is a structure so vast that light takes longer than the age of our own solar system to cross it. These walls and filaments are not static. The galaxies within them are in motion, and the structures themselves are slowly evolving under the competing influences of gravity, which pulls them together, and the expansion of the universe, which pulls everything apart. They are the scaffolding of the cosmos, the framework upon which the universe is built. To the mind, these structures are almost pure concept. Their scale transcends any familiar analogy. They are not places one could visit, but are instead patterns in the distribution of matter, revealed only by mapping the positions of hundreds of thousands of galaxies. They represent the ultimate triumph of order over cosmic scales, a delicate and beautiful cosmic tapestry. Just as significant as the filaments and walls are the immense regions of near-total emptiness that they enclose. These are the cosmic voids. They are vast, spherical or elongated regions of space that contain very few, if any, galaxies. They are the great deserts of the universe, the dark counterpoint to the bright filaments of the cosmic web. The typical diameter of a void is around 100 million light-years, but some are much larger. These are not regions of absolute nothingness, but rather areas where the density of matter is exceptionally low, far below the cosmic average. The few galaxies that exist within them are often called void galaxies, lonely systems in an ocean of emptiness. One of the largest known voids is the Boötes Void, sometimes called the Great Nothing. It is an enormous, roughly spherical region of space with a diameter of nearly 330 million light-years. In a region where one would expect to find thousands of galaxies, astronomers have so far identified only about 60. The environment inside a void is one of profound isolation and stillness. The temperature of the intergalactic gas here is close to absolute zero. The gravitational influences are minimal. A galaxy residing in the center of the Boötes Void would have no visible galactic neighbors. Its night sky would be almost entirely dark, save for the faint, distant glow of the surrounding cosmic walls. The existence of these voids is a natural consequence of how cosmic structure forms. In the early universe, tiny quantum fluctuations meant some regions were slightly denser than others. Gravity amplified these differences, pulling matter from the less dense regions into the denser ones. The dense regions became the filaments and clusters, while the emptying regions became the voids. The process is like making a foam. The soap and water are analogous to the galaxies and dark matter, while the air bubbles are the voids. Over time, gravity causes the soap film to drain and collect in the junctions between the bubbles, making those junctions brighter and the bubbles themselves larger and emptier. The universe has arranged itself in this same, efficient way. At this ultimate scale, the universe becomes a simple, repeating pattern. Bright, dense walls and filaments, woven into an intricate web, surrounding vast, dark, and quiet voids. The individual details of stars, planets, and even galaxies have faded into insignificance, resolved into a single, grand, and tranquil structure that fills all of observable space. The mind, having journeyed across these unimaginable scales, can now let go. The frantic details of daily life are rendered infinitesimally small against the serene and silent backdrop of the cosmic web. There is no more distance to travel, no larger structure to comprehend. There is only the quiet, rhythmic pattern of the universe itself. Our perspective now settles, pulling back to a final, all-encompassing view. We see the universe not as a collection of objects, but as a delicate, luminous pattern. The cosmic web, with its bright filaments and dense nodes, is suspended in an ocean of profound darkness, a tapestry of light against an infinite backdrop of quiet. Our attention is no longer drawn to the bright threads of this web, but to the vast, empty spaces between them. These are the cosmic voids, the great, quiet oceans of the universe. They are not the exception, but the rule. The vast majority of the universe's volume is this silent, tranquil emptiness. A void is a region of immense scale, a realm of near-perfect stillness. To journey through one would be to experience an isolation beyond human comprehension. The few lonely galaxies that reside here are like single, solitary ships on an ocean wider than 100 million light-years. The silence is absolute, the darkness near total. Inside a void, the night sky would be an almost unbroken black. The brilliant river of the Milky Way would be absent. The faint smudges of neighboring galaxies would be gone. There would be only the most distant, faint points of light from the cosmic walls, their ancient photons having crossed unimaginable gulfs of space to arrive. The existence of these voids is the natural result of the universe's patient sorting process. Over billions of years, gravity has gently herded matter together, drawing it out of these regions and into the filaments and clusters. The voids are simply what is left behind when this cosmic settling is complete, a state of deep and lasting peace. The mind, having journeyed across these structures, can now find rest in their absence. There is no more distance to travel, no larger structure to comprehend. There is only the serene and silent pattern of the universe itself, a balance between the something and the nothing, between the light and the quiet dark. And so, the mind is invited to float in this gentle emptiness, to let go of the dense clusters of thought and drift into the quiet voids of awareness. The frantic motion of the day can settle, finding its place in a stillness as vast as the cosmos itself. There is no need to hold on to anything. In the quiet space between the galaxies, there is only stillness. In the vast, gentle dark of the void, there is only peace. The cosmic web fades into a soft, background hum, a gentle and distant rhythm that does not need our attention. The details of the world can now become as distant as the farthest stars. The body can feel weightless, suspended in this calm and endless space. Each breath is a slow, easy tide, rising and falling in harmony with the silent, patient rhythm of the universe. There is nothing left to hold on to. There is nothing left to figure out. The story has been told. The journey has been taken. All that remains is this quiet, this immense and peaceful dark, a space for the mind to finally be still. All that remains now is rest, the deep, untroubled rest that comes from understanding one's small place in a vast and strangely peaceful whole. A quiet mind in a quiet universe. Let the mind drift now, in the calm of the cosmic quiet.